All right, so for this example, we got the electric field lines drawn in the direction that a positive test charge would go in this region, and that's outward, okay? But we can also draw the potential, right? How much potential a charge will have, right? As it has its force exerted on this positive test charge, it will have an unbalanced force, it will be accelerating outward, and its potential will change, right? It will move from one potential to another, experience a potential difference, some work will be done, and it will speed up, right? So that means that we can draw what are called equipotential lines around here, right? At different distances, a test charge would experience different potentials, right? So just like in our previous example where I drew those horizontal green lines, these are circular green lines because anywhere along here, a test charge would have a certain amount of energy, right? A certain potential. Anywhere along this green line, a test charge would have a different amount of energy and a different potential, right? Depending on its distance from that charge and whether the charge was positive or negative. So each ring has its own potential, okay, V. And for a point charge, you calculate the potential at any point around that point charge as Coulomb's constant, times the charge Q over R. And I'm leaving off the absolute value signs for this because you will get a negative potential for a negative charge and a positive potential for a positive charge. And that can indicate what direction a positive test charge would be moving. Okay, this Q is this guy here. A positive test charge would be moving. So a positive test charge would be moving away from a positive central charge, but it would be moving towards a negative charge. Okay, so there'll be a difference in sign there. So to find the potential difference, you'd actually, let's say we had a charge that was right here. Okay, and then it moved right here. Right, so we could call this position 1, and we can call this position 2. And for both of these, you would just do the potential at position 1 equals K times Q over R. And R would be the distance from the center out to that point. Okay, so we call that R1. Okay, and then we have this other charge that's at position 2, or that same charge, if it's at position 2, it would have a potential 2 equal to K times Q over R2. Again, where R2 would be the distance from the center of this charge out to this location here, R2. Okay? And then if you wanted to find the potential difference, right, you would take the potential at position 1 minus the potential at position 2, right? Or vice versa, depending on which one is a larger value. Okay? So that's how you find the potential difference. For a point charge, right, you just find the individual potential at two different locations and you subtract them to find the potential difference. Okay, and then finally, I would like to have us develop one more graphic organizer for charges. So we'll look at forces acting on point charges versus forces, voltage and electric field due to parallel plates. Okay, so let's look at forces first. So to calculate the force that's exerted on between any 2 point charges, we use Coulomb's law here. Force equals K times Q over R squared. Okay, and I'm going to use the capital Q lowercase q notation where you typically have a large charge and then a smaller test charge. That's not always the case, but it's most often the case. All right, you'll notice parallel plates, there isn't a specific equation that you can use to calculate force, but you do have that definition of electric field strength, which is the force per unit charge, and the charge we're talking about is the test charge that would move in that region. So if you wanted to calculate force, you could just rearrange that as E times Q. All right. So this is the definition of an electric field. So these are kind of overarching. Electric field strength is the same. You can use the same equation for parallel plates and point charges as a definition. If you're calculating the electric field due to point charges, it's K times Q over R squared. For parallel plates, the electric field strength is the potential difference between those 2 plates, and this D is the plate separation. Okay, so if you had 2 plates, right, if one plate was 10 volts and another plate was 0 volts, right, you'd find the potential difference. And if they were separated by 10 centimeters or 0.1 meters, you would have 10 volts over 0.1 meters, and you get an electric field strength of 100 volts per meter, right, as an example. Okay, so this is for finding the electric field strength between 2 parallel plates, and this is a constant electric field strength between those 2 plates. Electric potential or voltage, you can calculate that like we just did in the example for a point charge. Between parallel plates, there's not really an equation that you can use to calculate the voltage at a particular place, but there's a tool called a voltmeter that we can use to make that measurement. And then we'll be doing that sort of measurement when we work in the circuits unit at the beginning of next year. All right, and then finally, potential difference. The same equation works for both point charges and parallel plates. Potential difference is the difference in electric potential energy, literally subtracting 2 voltages. That is equal to the change in electric potential energy per charge, also known as the work done per unit charge. And please don't forget that we can rearrange this equation to be delta V times Q, right, is equal to the work done, which is equal to 1/2 mv squared. Okay, tattoo that on the inside of your arm, stamp it under your eyelids, whatever you need to do. It's super important. Okay, so today we're going to do some review. If you haven't tried some of these problems, please do so. I believe I posted them on the Google Classroom last week. If not, apologies. But take a look at those and let me know if you have any questions. Also take a look at questions from former IB exams on the Google Classroom related to the topics that we've been studying of field forces. And let me know if you have any questions. All right, have a good week.